Okay. So previously, we have considered the cat vector, which is basically a column vector. And consider two different kinds of product. Inner product which is like x and y, and outer product. So inner product is between, it's actually, the result is real number or complex number. And outer product is you produce n by n matrix. And of course, we have also considered a determinant. Determinant in terms of cofactors and minors. So for example, if we have A11, A12, A13, A14, A21, A21, A22, A23, A31, 32, 33. Determinant A is basically I, J, K, epsilon I, J, K, A1I, A2J, A3K. And it does have a name. This symbol has a name called Levi-Civita. A11 is plus sign, A22, A23, A12, A23. Let me see, 1, 2, 3, counterclockwise. A31 plus A13, A21, A32 minus. Minus sign is according to the odd permutation. A11, A23, A32 minus A13, A22, A31 minus A12, A21, A33. 2, 1, 3, right? So for 3 by 3, actually, the rule is very simple. You said it's 1, 2, 3, right? And second is I, J, K, determined by this Levi-Civita symbol, which is plus 1 when it's even permutation, and minus 1 when it's odd permutation. So you just write down 1, 2, 3, or 3, 3. That must be 3. So you just write down 1, 2, 3, and then choose the second index, which is the column index, according to this rule. So it's counterclockwise or plus. So 1, 1, Next is 2, 2, 3, 3, right? And 1, you can set this 2, 3, 1. So 1, 2, 2, 3, 3, 1. Or start with 3, 1, 2. 1, 3, 2, 1, 3, 2. If it is clockwise, it's called odd commutation and gives a minus sign. So A1, 1, A2, 3, A3, 2. A1, 3, A2, 2, A3, 1. And finally, A1, 2, A2, 1, A3, 3.
So this is even, this is odd.
So for 3 by 3 matrix, determinants can be calculated rather easily. Well, same rule can be applied to the following. You can determinant A, A11, A12, A13, A21, A22, A23, A31, A32, A33. So this direction gives plus. And this one plus this 2 plus. This is even permutation. This direction is minus. So it becomes this one is minus. This becomes minus. That's a graphical rule. You obtain the same result. Right? So can you feel the second index? 1, 1, 2, 3, right? This is plus. So this is 1, 2. Actually, this is the easiest. 1, 2, 3. 2, 3, 1. Right? 3, 1, 2. Which is plus. Minus sign is in this direction. 1, 3, 2. 3, 2, 1. 2, 1, 3, right? So for 3 by 3 case, determinant is very easy. You just follow which one is even or which one is odd.
So this is even permutation. This is odd permutation.
If the matrix size is larger than 4, then it is a little bit complicated. Probably the easiest way is using cofactor for 4 by 4 is 3 by 3, right? You can expand the 4 by 4 matrix in terms of 3 by 3 matrices. So let me see. Just think. Maybe I'll just show you the simplest case. So 4 by 4, the easiest way is using maybe just using cofactor and minor. Otherwise, you can use the Leibniz with the symbols, which one is plus and minus, but
It's a bit complicated. We have how many cases? Four factorial, right? 24 cases. So then maybe you can actually program the computer. It's easier, but just if you try to use hand, but you have to case all 24 different cases. So probably just using the minor and cofactor would be easier. So am I going a little bit too fast? No, it's okay. So for your own benefit, I'll just try to find the determinant for 4 by 4. Say, let's choose some simple cases. Maybe 1, 0, 1, 0. 0, 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0. It's a little bit. I tried to put as many zeros as possible. About half of the element are 0, right? So let's try to expand with the first row. Then we need to use 1, M11. M11 is you delete this, right? Zero, 1, 0, 0, 1, 1, 1, 0, 0. So let's try to calculate this. So this is, using simple rule, you can expand. Let's try. This is 0, right? How about this? How about this? All 0. This, -1. This, 0. This 0, right? So M11 is -1. So C11 -1 to the 1 plus 1, M11 is -1, right? We don't need the M12, right? Because this is 0. We probably need only this one, M13. This and this. Zero, 1, 1, 0, 0, 1, 1, 1, 0. So let's see. This is 0, right? This is 1. This is 0. This is 0. This is 0. This is 0. So M13 is 1. So C13 is -1 to the 1 plus 3. M13 is 1, right? So determinant A is actually A11 C11 plus A13 C13. Uh-oh. So A11 is 1, right? C11 -1. A13 is 1. C13 is 1. So it's 0, right? So in this case, determinant A is 0. So can you find the inverse matrix or not? No, right? So inverse matrix doesn't exist. So this is one case. So maybe I can give you homework. Design 3 4x4 matrix and find the determinant and inverse matrix. So 4x4 can be a good, like a cases to practice to calculate the determinant. Let's design three different pieces of matrix by yourself. And first find the determinant. Second, find the inverse matrix. As is the usual case, you don't have to submit the homework, you just do it at home. So when is the best time to do homework, do you think? This is actually supposed to be a joke. The best time for doing homework is when you are stood up, at the blind date. blind date is 소개팅. And stood up means 바람 맞다. So you are waiting at the blind date. Waiting for 1 hour, and you're supposed to be your date doesn't show up. So what do? Homework. If you design 4x4 matrix, this is probably one of the best ways to spend 1 hour. So even if you are stood up, you still feel good, right? Because you have done your homework. It's supposed to be a joke. Any questions? So next topic is eigenvalue problem, which is actually a very important problem, such that A so this is called eigenvector. This is called eigenvalue. This is German. Eigen is German. It means characteristic. So you can actually transform this A lambda I minus lambda I is equal to 0, or A minus lambda I identity matrix lambda I is equal to 0. So let's call this A prime. If determinant of A minus lambda I is non-zero, what happens? Inverse exists, right? Then inverse exists. And as a result, lambda I is supposed to be all zero. Which is called null vector. Null means zero. Mathematical definition. You will sometimes say 널널하다, right? 널널하다 means you have nothing to do, right? Or you have zero things to do. So null is actually, that means null means zero. But the only possible solution is zero null vector, then it's not very interesting, right? So this is called trivial solution. And not very interesting, not very exciting. So condition for the existence of solution for the eigenvalue problem is determinant A minus lambda I is non-zero. This is condition. Zero. Sorry. Zero, right? Condition for the existence of the solution for the eigenvalue problem. You are going to find out the determinant of lambda is equal to zero. And we are also going to confine our matrix, which is Hermitian matrix. Just an example. A 0, 1, 1, 0. This matrix must be familiar to you because we considered this the last time. And we are going to consider the Hermitian matrix only for now. Then A minus lambda I is 0, 1, 1, 0 minus lambda 1, 0, 0, 1 is minus lambda 1, 1 minus lambda, right? So determinant A minus lambda I is lambda square minus 1 equal to 0. Lambda is plus minus 1. So let's say lambda 1 equal to 1, lambda 2 equal to minus 1. This is somewhat familiar to the last case, right? So when case 1, lambda 1 is equal to 1, then A, say, we set lambda as AB, some number. Then A lambda is lambda, right? So 0, 1, 1, 0, AB equal to, that is BA equal to AB. So A equal to B, right? So if lambda 1 A equal to A square plus A square is equal to 1. If we set A is 1 over square root of 2, right? So lambda 1 is square root of 2 over 1, 1. Something familiar. For lambda 2 is minus 1. Set lambda 2 as CD. Then A lambda 2 0, 1, 1, 0 CD equal minus lambda 2, right? Minus of CD, which is TC. As a result, T equal to minus C. So we normalize lambda 2. That means lambda 2 is equal to C minus C, C minus C equal to C square plus C square equal to 1. So C is again 1 over square root of 2. So lambda 2 is equal to square root of 2, 1 minus 1. This story, this scenario seems to be familiar from the last class, right? And maybe you are curious why I have chosen particular number 1 and minus 1. And that is actually turns out to be eigenvalue of that particular matrix. So we have lambda 1 equal to 1, lambda 2 equal to 1. How about lambda 1, lambda 2? Which is square root of 2, 1 minus 1, square root of 2, 1, 1, which is 1 half, 1 minus 1, 1, 1 is equal to 0, right? So they are actually orthogonal to each other. So the word ortho is from Greek. Prefix. It's called a prefix. Greek, which means straight. The typical case is orthodontist, orthopedic. There's another Greek word, means bone. So orthopedic is a orthopedician, or it's a medicine. It's a branch of medicine that straighten, fix the bone, right? Bone problem. 정형외과, orthopedic, or doctor is orthopedician. So pedic is a Greek word, means bone. So from this, another branch of medicine is pediatrician. Pediatric. Pediatric is called 소아과 because young kids easy to break their bones, right? And the doctor means pediatrician. Another word came from ortho is orthodontic. This means teeth. The orthodontist is 교정. Orthodontist is the practitioner who is fixing your teeth. And dentist actually came from that word. So if you study the origin of Greek word, then you can actually learn many other English words. Well, it turns out somehow my mathematics course became English class. It's just a sidetrack. But probably I hope you learn some few useful TOEIC words. So lambda 1, outer product. Square root of 2, 1, 1. Square root of 2, 1, 1. Which is 1/2, 1, 1, 1, 1, right? Lambda 2, 1 minus 1, 1 minus 1, 1/2, 1 minus 1, minus 1, 1. So lambda 1 plus lambda 2 is equal to 1, 0, 0, 1 is identity, right? And lambda 1, lambda 2 is plus 1, 1/2, 1, 1, 1, 1 minus 1/2, 1 minus 1 minus 1, 1 becomes 0, 1, 1, 0 is equal to A. And this is called spectral theorem. So let's summarize some of the properties of Hermitian matrix. Sorry, Hermitian. Eigenvalues are real number. Eigenvectors identity. This is called spectral theorem. Here, orthonormal set. Then, interesting thing is, you can calculate a square, which is I, j, lambda I, lambda j, lambda I, lambda j, what is this? Delta ij, right? So this inner product is when I and j are different to 0, and I and j are equal to each other, then it's 1, right? So this is actually summation of ij, but only one I survives. So this is basically and then actually you can continue this. You can multiply a many times. And a to the k lambda I to the k lambda I lambda I. So when a is equal to 0, 1, 1, 0, what is a to the 100? This is minus 1. Then you know the answer, which is 1 to the 100 is 1, right? Minus 1 to the 100 is again 1. So the result is identity. Over 100, 101 is plus 1 to the 100, 1, lambda 1, lambda 1, plus minus 1 to the 100, 1, lambda 1, lambda 1, which is simply lambda 1, lambda 1, minus lambda 2, lambda 2, sorry, which is A, right?
The spectral theorem allows to the matrix product of a given Hermitian matrix very efficiently.
So if I ask you to calculate A to the 1,000,001, so A is simply 2 by 2 matrix. So multiplying A by A takes maybe 1 second, right? So if we just do this brutal force by a million times, how many times will it take? A million seconds, right? Million 1 second. 1 day is how many seconds? 36 seconds for 1 hour. Times 24 is close to 10,000. So if you keep multiplying, it's simply 2 by 2 matrix 1 million times, it will take 100 days. Right? If you do not know the spectral theorem, then you have to spend 100 days to simply multiply a million times. But since you know the spectral theorem now, you know the answer immediately, which is simply A. All right? The spectral theorem. Maybe you can take a break for maybe a few minutes. Let's consider another special case. So this matrix is also Hermitian. M adjoint is 125 minus 75 minus 75, 125 is M, right? So M is a Hermitian matrix. Okay, probably I should try to write down slowly because my handwriting is not very good. So let's try to find out the eigenvalue first. Determinant m minus lambda I 125 minus lambda minus 75 minus 75 125 minus lambda, right? So 125 plus 75 minus lambda, 125 minus 75 minus lambda, 200 minus lambda, 50 minus lambda is equal to 0, right? So lambda is either 50 or 200. So what is the major difference between this matrix and the previous one? The previous matrix has eigenvalue which is 1 and minus 1. In this case, 50 and 200, which is all positive, right? So this is very important. So M is also a positive matrix. We call a particular matrix a positive when its eigenvalues are positive. So M is a Hermitian matrix, positive Hermitian matrix, because its eigenvalues are all positive. On the other hand, the previous matrix, A or X, which is not positive because one of the eigenvalues is minus, right? Need time to copy? Perhaps I'm going a little bit too fast. So lambda 1 is 50. Oh. Lambda 1 is 50. Say lambda 1 AB as previously. M lambda 1 50 lambda 1, right? So 125 minus 75 and 75 125 AB is 50 AB. So 125A minus 75B is 50A minus 75A plus 125B is 50B. But the results are the same. Simple. A equal to B, right? So normalized eigenvector square root of 2 over 1, 1. How about lambda 200? So m lambda 2 is 200 lambda 2. Let's say lambda 2 vector as a CD. Then 125 minus 75 minus 75, 125 CD 200 CD. So 125 C minus 75 T is 200 C, or minus 75 C plus 125 D is 200 D. So which means D is equal to minus C. So even though we have different eigenvalues, we still get the same form for the eigenvector, right? So lambda 2, you can say square root of 2, 1 minus 1, right? So we have lambda 1, lambda 2 as orthonormal basis. Sometimes we call basis as a means set. So lambda 1 is square root of 2, 1, 1. Square root of 2, 1 minus 1. I'll just give you some time to copy. This is a very interesting matrix. So lambda 1, square root of 2, 1, 1, right? Lambda 2, square root of 2, 1 minus 1. Lambda 1 is 50. Lambda 2 is 200. Lambda 1 is 1 half, 1 half, 1, 1, 1, 1, right? Lambda 2, 1 half, 1 minus 1, 1 minus 1, 1 half, 1 minus 1, minus 1, 1. Let's check the spectral theorem. $50 over 2, 1, 1, 1, 1. 200 over 2, 1 minus 1, minus 1, 1. Simply 125, 125, minus 75, minus 75, right? Which is M. This is spectral theorem, right? Since M is a Hermitian matrix, we just saw that the spectral theorem is satisfied. So symbolically, we can just make a summation. You can write this way. 2 × right? That's the spectral theorem. But beauty of the spectral theorem is you can actually represent the matrix functions as well. So m square lambda I square blah 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 m to the k then we can also represent some function of matrix. This is actually also generalized spectral theorem. This is very important. So you can represent the original matrix in terms of spectral theorem. Summation of the output product weighted by the identity. Then you can M2, right? And scale k times M to k, or lambda I to k. And you can generalize some function of n. Simply put it as lambda. Then you can actually calculate the square root if when all lambda I is greater than 0, you can represent the square root of m as a square root of lambda I or logarithmic m or log e to the m so you can actually calculate the logarithmic of a matrix or square root of matrix using spectral theorem, so which can be a very powerful tool. So let's try to calculate the log m. It's a bit weird concept, right? Of calculating the square root of matrix or some logarithmic function of matrix. But actually you can do for particular square matrix when the eigenvalues are positive. So for this matrix, let's try to see what is the square root. So m was 125 minus 75 minus 75, 125. We have lambda 1 is 50, lambda 2 is 200, eigen 1, 1, lambda 2, square root of 1 minus 1. The square root of m is simply square root of 50, 1 half, 1, 1, 1, 1, square root of 200, 1 half, 1 minus 1 minus 1, 1. That is 25 times 2, square root of 2 over 5, 1, 1, 1, 1. That is square root of 2 over 10, right? 1 minus 1 minus 1, 1. So square root of 2, 15, 15, minus 5, minus 5, or maybe 5 over square root of 2, 3, minus 1, minus 1, 3. This is weird or amazing that you can ever calculate the square root of omega. Let's check. What is this? Root to m times root to m. 2 over 25, right? 3 minus 1 minus 1, 3. 3 minus 1 minus 1, 3. It's 2 over 25. This is 10, right? And this minus 6. 125 minus 75, 125 is m, right? So this matrix is actually indeed square root of this, right? Because you multiply this twice, you obtain is already 10%. This is a bit weird concept, but the square root of matrix is useful tool. And that is only possible when eigenvalues are all positive, right? So when you have a Hermitian matrix with positive eigenvalues, then you can calculate the square root. And also you can calculate the logarithmic function as well. Am I going a little too fast? It's okay. Are you following me? But this is a new concept because nobody has, you probably didn't think that the square root of matrix is possible. So it's just a way of extending the numbers, like let's spend some more time for the eigenvalue problems. So, because mainly we have been doing 2 by 2, maybe just one more example for 3 by 3. So any questions about the square root of matrix? So how many of you have heard about
the square root of n? No one, right? So probably the first time we learned about this.
1, 1, 0, 1, 0, 1, 0, 1, 1. Let's check whether this is Hermitian or not. A adjoint. 1, 1, 0, 1, 0, 1, 0, 1, 1, A, right? So this is Hermitian matrix. So this notation, if we have magnifying glass, will become something like this. Dagger.
So adjoint operator is project with dagger. Right? Dagger.
So determinant of A minus lambda I is determinant of 1 minus lambda 1 0 0 minus lambda 1 0 0 1 minus lambda. Let's try to calculate this first. Minus 1 minus lambda 1 minus lambda lambda. This is 0, right? This is 0. How about this is 0? This is 0. And this one. Minus 1 minus lambda, right? Or you can put lambda minus 1, 1 minus lambda lambda plus lambda minus 1. Minus lambda something is odd. Must be 2 minus lambda. So 1 minus lambda, 1 minus lambda, lambda. And this is 0, this is 0, this is 0. This 0, this 1 minus lambda. Lambda minus 1, lambda minus. Something is odd. Oh. 1, 1, 0, 0, 1, 1. 1 minus 1 minus lambda 1, 0, 1. minus, oh, minus square. This one? All right, this has to be 1, right? Let me see. 1. This one? Yeah? 1 minus lambda, 1, 1. 1, lambda 1. I think I made a mistake. Let's check. So we have, okay, I must be getting old. 1 minus lambda. And this is 1, so we have, again 0. So, but because this is 1, we have minus 1 minus lambda and minus 1 minus lambda, right? Okay. So that is minus 1 minus lambda, 1 minus lambda, lambda minus 2, twice of 1 minus lambda. Okay. So minus 1 minus lambda, 1 minus lambda, lambda plus 2. Minus 1 minus lambda, 2 plus lambda minus lambda square, right? So becomes 1 minus lambda, lambda square minus lambda minus 2, which is 1 minus lambda, lambda plus 1, lambda minus 2. Okay, good. So lambda is equal to minus 2, plus 2, 1, minus 1. Okay, so this is called dumb mistake. So actually it slowed down. I made a small mistake here. So we have 3. A, maybe I just use blue. A is 1, 1, 0, 1, 0, 1, 0, 1, 1. Lambda 1 is 2. Lambda 2 is 1. Lambda 3 is minus 1. So let's try to find out the eigenvectors. So set lambda 1 is A, B, C. Then A lambda 1 twice of lambda 1, right? So 1, 1, 0, 1, 0, 1, 0, 1, 1. A, B, C is A plus B, A plus C, twice A, B, C. So A plus B is equal to A, or A equal to B, right? B plus C is 2C, or B is equal to C, right? So lambda 1 is basically A. So let's try to make out lambda 1, A, 3A squared equal to 1, right? So A is square root of 3. So lambda 1 can be square root of 3, 1. How about lambda 2 is equal to 1? I will let you copy. Lambda 2 is plus 1. Is this matrix positive or not? One of the eigenvalues is negative, so it's not positive matrix. A lambda 2 is lambda 2. So lambda 2 is DEF 110, 101, 011, DEF T plus E, T plus F, E plus F equal to TEF. T plus E equal to T. E is equal to 0. T plus F is equal to 0. F is minus T, right? So lambda 2 is 0. No. T, 0 minus T, right? So T must be square root of 2. Lambda 2 must be square root of 2, 1, 0, minus 1. I still copy? Lambda 3 is lambda 3 minus 1. Minus 1, so let's say lambda 3 xyz. So A lambda 3 minus lambda 3, 110, 101, 011, xyz is x plus y, x plus z, y plus z is minus of xyz. X plus y is minus x. y, x plus z is minus y plus z is minus c. So y is minus 2x equal to minus 2z, right? So this y equal minus 2z. And it's x, y equal x. So it looks like lambda 3 must be of the form y x plus y is minus x, so y is minus 2x. And z must be same as x minus 2x, x, right? So lambda 3 must be square root of 5, 1 minus 2, 1. Square root of 6. One plus 4 plus 1 is 6. Complicated. So summarize. Lambda 1 is 2, and eigenvectors are square root of 3, 1, 1, 1. Lambda 2 is equal to 1. Lambda 2 is square root of 2, 1, 0, minus 1. Lambda 3 is minus 1. Lambda 2 is square root of 6, 1 minus 2, 1, right? Let me double check. So let's check this. 1 over 3, 1, 1, 1, 1, 1, 1. 1 over 3, 1, 1, 1, 1, 1, 1, 1, 1, 1. Lambda 2, 1 over 2, 0, 1, 0, minus 1, 1 over 2, right? 1, 0, minus 1, 0, 0, 0, minus 1, 0, 1. Lambda 3, 1 over 6, 1, 2, 1, 1 minus 2, 1. 1 over 6, 1 minus 2, 1, minus 2, 4 minus 2, 1 minus 2, 1. Let's add them together. Lambda 1 plus lambda 2, lambda 2, lambda 3, lambda 3. What happens? Three, 1/2, 1/6, right? And second element, 1, 3 minus 2 over 3. 1, 3 minus 1 over 2 plus 1 over 6. 1 over 3 minus 2 over 6. 1 over 3 plus 4 over 6. 1 over 3 minus 2 over 6. 1 over 3 minus 1 over 2 plus 1 over 6. 1 over 3 minus 2 over 6. 1 over 3 plus 1 over 2 plus 1 over 6. So this is what? 1, right? This is 0. This is 0. This is 0. This is 1, 0, 1, 0, 0, right? So if we add them together, we have 1, 0, 0, 0, 1, 0, 0, 0, 1, which is identity. Let's check the spectral theorem. So we need to copy this again. Copy, paste, paste. Spectral theorem, check the spectral theorem. Lambda 1, lambda 2, lambda 3, right? So lambda 1 is 2, so there's 2 over 3, 1, 1, 1, 1, 1, 1, 1, 1, 1. Lambda 2 is plus 1, so it is 1/2, 1, 0, minus 1, 0, 0, 0, minus 1, 0, 1. Lambda 3 is minus 1, so 1 over 6, minus 1, 2, minus 1, 2, minus 4, 2, minus 1, 2, minus 1, right? Two over 3 plus 2 minus 1 over 6. 2 over 3 plus 2 over 6. 2 over 3 minus 1/2 minus 1 over 6. Two over 3 plus 2 over 6. 2 over 3 minus 4 over 6. 2 over 3 plus 1 over 6, right? over 3 minus 1 over 2 minus 1 over 6, 2 over 3 plus 2 over 6, 2 over 3, 1/2 minus 1 over 6. Okay. This is 1. This is 1. This is 0. This is 1. This is 0. This is 1. This is 0. 1. 1, right? So 1, 1, 0. 1, 0, 1. 0, 1, 1 equal A, right? So that means spectral theorem is satisfied. So we have seen that 3 by 3 Hermitian matrix, again, the spectral theorem is valid. So during this, my class, I have shown that for 2 by 2 Hermitian matrix, you can see that the spectral theorem is satisfied, and 3 by 3 Hermitian matrix, also spectral theorem is satisfied. I have shown that only for special cases, but now you can trust me that the spectral theorem will be valid for any n by n Hermitian matrix. And even though I have shown only for 2 and 3-dimensional cases, but it's generally true for n-dimensional cases. If you have a faith. So, but actually we can extend it to 4 by 4. So this time I may give you another homework. For given design, maybe just one will be enough. 1 4 by 4 Hermitian matrix. Show the spectral theorem. It's true. This is what homework means. You do at home, but don't give it to me. Just for your own benefit. I think we have done enough for today, so maybe we can stop. Actually, I have one more topic, but maybe we can save it for the next time. Yeah.
스펙트럴 기호로 더해서 I 되는 거 아니에요? 그것만 스펙트럴 기호.
네, 맞아요.
그리고 이거 같은 경우는 스펙트럼표로 일반적으로 사용하는 네, 그 지수가 지수는 공수할 상관없어요.
네, 이거 여기는. 근데 이제 루트를 구하려면 우리가 플러스에 루트를 구하려면
네. 그리고 이거 캐팩터예요. 캐팩터 안에 있는 람다 i는 그냥 캐팩터의 이름인가?
네.
캐팩터 막 노멀라이즈 되어야 되거나 그럴 필요는 없어요.
여기서 노멀라이즈 해야 돼.
그 여기서 노멀라이즈 돼야 되는데
인간적으로 그래서
그렇죠.
이거 좀 편한 게 아이겐밸리랑
그렇죠.
같이 인덱스 쓰는 게
그러면 이게 정해지면 이것도 정해지는 거죠.
그렇죠. 어조인
건축에 있고. 그리고
일단 해보니까 물티도 갈 수 있다.
이거는 왜 성립하냐면 제곱일 때 성립하는
이거요?
네.
앞에서 했는데 곱해주면은 여기 람다 I 람다 J 이거 있잖아요. 람다 I 람다 J인데 이거가 연습이 되는 거잖아. 이거는 이제 I랑 J랑 합치면 1, 다르면 0. 그럼 그러니까 람다 I 제곱에 람다 I 람다
아까 이거 구할 때 C 람다는 임의로 주는 람다.
네,
임의로 줬으면 그래서 람다 1, 2, 3가 이렇게 값이 나온다면까지 나오는데 밑에 람다 1에 이런 식으로 구하고 이게 왜 이건 항상
1로 만드는 거예요.
이렇게 하면 항상 1이 나오는 값이.
3의 1이고 1이 되도록 A를 좋아해요.
그러면 그럼 지금 이거를 행렬로 나타낸 게 아니라 그냥 이거 다 그냥 서로 주는 별개인 건가요? 그러면 얘를 이런 식으로 브레이크에서 나타내면 이렇게 나타나서 이거를 이렇게 취하면은 항상 1이 나오는 거예요.
네, 1이 되도록 하는 거죠. 일단 유튜브를 또 보세요.
행렬에 이거로 일단 이쪽은 연관이 있다는 말씀.
네, 그렇죠.
그럼 이거를 이렇게 나타내면 어떻게 그러니까 지금 이 상태에서 이 값을 어떻게 만들려는 거예요?
남자들 이런 거지. A의 30%밖에 못
아니 나도 엄청 따라가봤습니다.
네.
진짜 기만자들.
이렇게
나무를 때리는데 이게 중문을 혹시
받을 수도 있어요.
마음속
네,
깊은 곳은
주문 있는 경우는 그것도 안 해. 어려워. 주문이 복잡해지거든.
왜냐면 리얼 밸류만 가지면 된다고 하셨는데
충분히 나올 수 있어요. 충분히 나오는 경우는
질문하니까 좀 달랐어요.
스케일은 나올 수 있어요.
성능이 안 나오더라고 그러면 무조건 알차겠습니다.
네. 이제 뭐 저장만 하죠.